So let's talk about cylinders and quadric surfaces. So we know that equations that have both that involve an x, y, and z variable, they all create some sort of surface. And one type of surface that an equation could create when graphed is a cylinder. So if the most basic example of a cylinder is probably the one you're thinking of, where you have x squared plus y squared equals 9. And what that does is it creates a cylinder like this, right? So we know that it creates a cylinder like this, where each cross section has a radius of 3. It's like a circle with a radius of 3, and that's given by this equation. And z is not in this equation, so we know for every z value, the cross section, if you were to split it in half at any z level, it's just going to be a cross section with this equation, x squared plus y squared equals 9, or a circle with a radius. So and let me really quickly draw the axes here. But now if we were to think about this kind of surface, so let me draw on this. Let's say you were to graph I think it is y, or let's do z equals x squared. I think that's z equals x squared. That's a specific one. What that would do is it would create or if you were to graph, it would look like something like this, where you kind of have this parabola looking thing that's extended. You can imagine, right? If I were to draw the cross section like this, you would have a parabola that would extend kind of forever along the y-axis, right? And that makes sense. Y is not in our equation, so because of that, for every y level, you just get the parabola z equals x squared. So these are cylinders, because cylinders are consisted with these lines that we call rulings. So there are these lines that are parallel to some sort of axis, and they pass through this curve. So in the case of a cylinder, all of these lines are parallel to the z-axis. And what you notice is, well, hey, z is not in our equation. So there's these lines that are parallel to the z-axis, but z is not in our equation. Same thing here, right? For the z equals x squared, all of these lines, right, they're all parallel to the y-axis, right, along the surface, and y is not in our equation. And that should kind of make sense, right? If a variable is not in our equation, that just means that our shape will essentially, you have this z equals x squared parabola at y equals 1, and it's the same exact shape, right? The cross section is the same exact shape or curve at y equals 5, or y equals 3, y equals -3. So it's the same cross section for every y variable or y value, because y is not in our equation. So it would extend on forever, and you would get those lines that are essentially parallel to the y-axis because it extends along the y-axis. So hopefully that kind of makes sense. These are called cylinders. Like they're literally surfaces that contain these rulings that are parallel to some sort of axis. And what you notice is, hey, I guess an equation for a cylinder would not have one of the 3 variables. Now let's talk about quadric surfaces. So quadric surfaces are just the graph of an equation that follows sort of according to, I don't know if it's worth writing this all down, but I might as well. So a quadric would have a graph that's like ax squared plus by squared plus cz squared plus dxy, plus xz, or I guess yz, I guess that's how the book does it, yz plus, and then we have f, Jesus, xz plus gx plus hy plus, what's the next letter, iz plus j equals 0. And if you do some, you know, like the a's, b's, and all those are constants, and then the x and z's are you know, variables. But you can do some manipulation, some translation, some rotations, so you can get it into the form of either ax squared plus by squared plus cz squared is then equals 0, or you can get into the form of ax squared plus by squared plus iz is then equals 0 with rotation, translations, and such, right? So an example, so this is just telling you the form of a quadric surface. And you think about why it's called quadric, right? I guess it's kind of like a quadratic-ish equation in the sense that, you know, you have an x squared term, and like the leading variables, I forgot what you call it. I guess the degree of this equation is the second degree, right? So take the example of x squared plus y squared over 4 plus z squared is going to equal 1. So if you were to graph this, I don't know, let me just check this is showing up on the camera, because I kind of have, yeah, that's fine. Okay, so you would get a graph that would look a little bit like a football-ish thing. It would be like this, like I guess I should draw the traces and stuff. You would kind of have these kind of look like this. It's like this very round shape. It kind of looks like this. And you notice that, hey, because each of these terms are squared, it's going to be symmetric around each axis, right? Because if something's squared, right, whether you go positive x value or negative x value, the x squared term would be the same. So it's going to be symmetric, and the same goes for y squared, z squared, and so on. And another thing you notice is, well, hey, let's say what happens when z is equal to 0? Well, when z is equal to 0, then you have this x squared plus y squared over 4 term, which is equal to 1. Well, this is just, this x squared plus y squared equals 1 form. That's just the form of an ellipse, right? Because you have your a value and your b value, right? X squared over a squared plus y squared over b squared equals 1. And yeah, you have like an ellipse that forms on z equals 0. Or sorry, not z, well, this is not z equals 0. This is z equals 0. Hopefully you can kind of see this kind of ellipse that's being formed as a result. And then as you start increasing y, or as you start increasing z, right, you on the z plane, right, when z is kind of a constant, in the sense that, well, if I look at z right here, for this curve, each point on this part of the curve, the z is constant. It could be at like z equals 3. And I keep forgetting the little dash. I got to get in the habit of doing that. But if I were to like slice this by a plane, oh my god, it gets really hard to draw these things. But the point I'm trying to make here is that for like this z value right here, right, along this z value, all the z points are constant, but now z is not 0. It could be like z equals 3. So if I do 1 minus, right, if I do, let's do it like this, if I just rearrange this to 1 minus z squared, because I'm looking at the xy plane where z is a constant, it's still the curve of an ellipse, but now this term has decreased. And to get it, it's kind of hard to think, but to get it in terms of, to get it into our x squared plus y squared over 4, or to get it into the x squared plus y squared equals 1 form, what I have to do is I have to divide this by 1 minus z squared, right? So I essentially get this form, 1 minus z squared. This is all going to equal 1. So what is the point of showing you this? Well, as z increases, the ellipse that is formed on the xy plane will start being smaller because our a and b terms are going to get smaller. We're subtracting by z. And eventually you get to a point where z is equal to 1. Well, at z equals 1, your ellipse is not defined for that point and beyond. So because it's going to be either 0 or once z gets bigger, it's going to be negative. So there's no points after that. And I'm showing you this. I'm yapping about this because I want you to start thinking in terms of 3D, right? These are the kind of things you have to think about. What happens when x or when z is held constant? What happens when y is held constant, right? You could do the same thing for the x squared. You have your x squared plus y squared over 4. I forgot the 4 here, so sorry about that. But hopefully you get the point. Plus z squared equals 1. When y is equal to 0, right? When y is equal to 0, then you just get a circle. So that would look like something like this, right? On the xz plane. And then as your y gets bigger, when you subtract it over, right? Minus y squared over 4, this radius just ends up getting smaller. So it's the same on the yz plane. It would still be the same as we hold y constant on the xz plane, but the radius keeps getting smaller. So I just want you to start thinking about these surfaces like that. I think that'll just to understand, like, hey, what happens as x grows bigger? What happens to the cross section? And we call what we do is we call these kind of cross sections or whatnot, we call them traces. And traces, thinking like this, will help us graph a lot of quadric surfaces. So I'm going to do an example of graphing a quadric surface. Let's say we are trying to graph the graph of x. So let's say we're trying to graph, let me just erase all this stuff. Let's say we're trying to graph the graph of x. That's awesome. X equals y squared plus 4z squared. All right. So I'm going to use a couple different colors, so hopefully I can help with this. Also get this back. Actually, I guess I won't. I'll just use 3. How about that? Yeah, three color. Yeah, I guess I have 4, so I might as well use 4 colors to kind of help with this. We want to see, well, hey, what would the graph look like if we're only looking at the xy plane? So for the xy plane, what would yx plane, what would my graph look like? So for the xy plane, let's take the case when z is equal to 0, right? Well, when z is equal to 0, right, at that plane where z equals 0, that's in the xy plane, what would our graph look like? Well, this would be horizontal parabola, right? It opens up horizontally. So let's do it like this. So let's use green for z equals 0, right? So this is for z equals 0. Now what happens as z increases? Well, when z increases, what we can do actually to better understand this is we can arrange this into y squared is going to equal x minus 4z squared. And by rearranging it like this, you see that, hey, well, the z term kind of acts like a horizontal shift. So as z increases, you get this horizontal shift. So if we increase it to 1, right, we get y squared equals 4 minus 4, x minus 4. So this would be like right here. It would still be an opening parabola, but now we have this shift. Because z, right, in the xy plane, it acts like a constant. For every point on the xy plane, z is the same. So we can treat z like a constant. So we have z equals 1. And then let's think about y at z equals 2. Now it's going to be y squared equals x minus 2 squared is 4. 4 times 4 is 16. So x minus 16. So wow, that's going to like shift it all the way up here. Should kind of make sense, right? Because that z term is squared. So as z increases, the shifts will get farther and farther and farther away. So those were the yx traces. Now let's think about the XZ traces. And you're going to see in a second how this will help us. You'll see in just a second, I promise. So now for the let's take a look at let's do ZX plane. So for the ZX plane, right, we kind of actually get something very similar, right? We essentially get something very similar because we're going to see, okay, at y equals 0, we get x equals 4z squared. So this is really just the same kind of shape, a vertical kind of parabola or whatnot. But now it's just going to be, so if we multiply by 4, I believe that is a vertical shift. No, that's a I always have to think about this. I believe that is a stretch, a horizontal stretch, I believe, because this is really, if we were to rearrange this. I like rearranging the equation. That's probably like the third time this happened like this week. Rearranging, what the rearranging does is it just helps you graph it into something that you actually know. So if I were to rearrange this, I get like 4 or z squared. Oh my gosh, I keep dropping stuff. Z squared is going to equal x minus y squared. So this is, or x over 4, right? No, this is all of this divided by 4, I believe, yeah. So that's going to be a stretch, I believe. I believe that's going to be a stretch because now to get a z value of 1, x no longer has to be 1, it needs to be 4. Yeah, so that would be a stretch. Okay, if I'm wrong about that, please let me know. But the point is it's just a little bit more stretched, but the key idea is still there, right? Now, if this is z equals 1, or so now we're looking at y, right? So this is y equals 0. Let's look now for y equals 1. It's going to be a little bit shifted further. Doesn't matter exactly where, because that's not the goal. We're not like plotting this for point for point, but we're just trying to get an idea of the shape. And I know, oh my God, I'm so thankful that didn't drop. And now this is going to shift even further for y equals 2, because the shift term is squared by y. So now for the last trace, we're just going to look at the x or z y plane. This is probably the simplest because now this actually becomes a ellipse, right? This equation is in the form of an ellipse because you have x. Actually, we can get it better into a term of the form of an ellipse. You get, so if we have x equals y squared plus 4z squared, which we really get, if I divide all of this by x, which I don't think this is right notation, sorry about that. If I divide all of them by x, I get 1 equals y squared over x plus, and then I can bring the 4 down here as 1/4. So I get over 1/4 x. Now this is in the form of an ellipse where x serves as our a squared term, as well as, or x is our a squared term, and then 1/4 x is our b squared term. So when x is equal to 0, the ellipse is not defined, so we're not going to have a green marker. But for x equals 1, it's going to have an x value of 1. So we have 1 here, which is really root 1, but once again, we don't need a perfect shape. And then 1/4 times 1, that would be 1/2. So 1/2 on the z value. Main thing to just, once again, we're not doing point for point, but it's just important to know, hey, on the z value, this is going to be shorter. So this is for x equals 1. And then for x equals 2, it's the same thing. So we have now each of these each of the major axis and the minor axis will get larger because the x is increasing. So now it's going to be x equals 2, which is just going to be a larger ellipse. All right, so these are our traces. Now let's try to make it into an actual graph. So if I were to get my 3D graph going, first thing you want to notice is, well, what are my domain restrictions, right? For the ellipse, really it's defined for all x greater than it's assigned for all x greater than negative. It's assigned for all x greater than 0, right? There's no negatives, so and x can't. Well, x I guess technically can be 0. Actually, I don't know. Yeah, because it's like if x is 0 here, these terms will just end up being 0. So it's assigned for x. It's just when we divide by x, we don't account for that. So you know the shape needs to exist only on the x-axis, and yes, and that is also shown here. There's no points on the y-x or z-x plane where there's x is negative. So that's really our only domain restrictions, because y and z are defined for all points, z and x are defined for all, or z is defined for all points, same with y. That's our main domain restriction. So that's a good thing to like just remember. So let's draw our traces. So in the y-x plane, we have this parabola that opens up in the x direction. So we can draw that like so. And then same thing for z equals 1. It opens up like so. And you know, you don't really necessarily need to draw all of these traces. These are just to help you get an idea. You can even get an idea of what the shape is going to be already. But I just want to show you this process because it is kind of helpful. So it's going to intersect, like, these should really extend, but it's fine. You get the idea. Now so this was the XY plane. Oh, I drew this wrong, didn't I? Yeah, I'm so sorry. These are supposed to be raised up, right? Because, yeah, that's my fault. I was thinking too fast. But the idea is, well, now this is for z equals 1. So this is really when it's raised up a little bit. Like, so, which is, that's going to get kind of hard to draw. And then it's like, z is like so. So you kind of get a z value, I guess, here. Like that. Yeah, this is going to get kind of nasty to draw. But maybe you can kind of start visualizing the shape just based off that. If you think about the zx plane, let me at least erase some of this stuff so it's not too confusing. But now if you think about the zx plane, oh, this is an atrocious drawing. This is just an absolutely atrocious drawing. But bear with me. If you think about the zx plane, we also have parabolas. So, or we have these like concave, or what do you call them? Like, oh, horizontal parabolas. So then you have like this parabola right here, and I think now you can start to determine the shape because you have this parabola opening up this way, parabola opening up this way, and then last of all, I'm not even going to draw all the traces, it's just going to be a mess, but last of all, then you have these cross sections in the zx plane that kind of look like this. So all in all, if you you know, once you draw it out, or hopefully just try to visualize it honestly, because your drawing won't be perfect, you get a shape that kind of looks like this. You get this kind of a shape. And this shape is actually called, if I look at my little cheat sheet because I don't have that memorized, this is called an elliptical paraboloid. So this is called an elliptical paraboloid, where you have the terms where you have two of the terms that are squared adding up to the other term which isn't squared. Let me actually show you a little cheat sheet that you can kind of screenshot or do whatever you need. This is just straight from the book. But yeah, these are all the shapes: hyperboloids, hyperbolic paraboloids, cones, ellipsoids, hyperboloids. Yeah, I know this video is kind of hard to explain, but really it's all about visualizing. If you can understand how to visualize, understand how to think in terms of traces, holding variables constants, and seeing what shapes you can or what curves you get, I think you'll be in good shape. So yeah, thank you for watching.